Looks like we're live. All right. So I think. Do I have links? I think I do have links. So let's see. Um, very sure this is. We're just gonna do this. Okay. Nucleophilic additions on aldehydes and ketones. Okay. So basically, the plan is read this chapter, do all the problems, and then do the homework. All right. Alright, much of organic chemistry is the chemistry of carbonyl compounds. Aldehydes and ketones, in particular, are intermediates in the synthesis of many pharmaceutical agents, in almost all biological pathways, and in numerous industrial processes. So, an understanding of their properties and reactions is essential. In this chapter, we'll look at some of their most important reactions. Aldehydes and ketones are among the most widely occurring of all compounds. In nature, many substances required by living organisms are aldehydes or ketones. The aldehyde pyridoxal phosphate is a coenzyme involved in a large number of metabolic reactions. The ketone hydrocortisone is a steroid hormone secreted by the adrenal glands to regulate fat, protein, and carbohydrate metabolism. In the chemical industry, simple aldehydes and ketones are produced in large quantities for use as solvents and as starting materials to prepare a host of other compounds. For example, more than 50 million tons per year of formaldehyde is produced worldwide for use in building insulation materials and in the adhesive resins that bind particle board and plywood. I actually didn't know that. Acetone Yeah. Oh, interesting. Propane 2O is widely used as an industrial solvent. Only 8 million? I'm actually kind of surprised that so little acetone is made. Formaldehyde is synthesized industrially by catalytic oxidation of methanol. Okay, that makes sense. Because methanol is a primary alcohol. And so, yeah. And one method of acetone preparation involves oxidation of 2-propanol, produced by hydration of propylene, hydration of propylene. So, wait, let's get up chem rules. Chem rules is the best, bro. Wait, can we get system? Okay, so propylene. So propene. Why is that so slow? Then we just need to add H3O, Markovnikov product. Then we add something like Jones, and we get acetone. Pretty cool. Naming aldehydes and ketones. Aldehydes are named by replacing the terminal E of the corresponding alkane name with al. The parent chain must contain the CHO group, and the CHO group is numbered as carbon 1. Okay. I actually don't like that way of doing it, but like I don't know. Note in the following examples that the longest chain in 2-ethyl 4-methylpentanal is actually a hexane, but this chain does not include the CH. Oh, okay, yeah. So here, so let's get the. So methanal is just formaldehyde, right? Because it's C double bond O H H. So if we looked up yeah, and then ethanol is CH3 C double bond O H. Okay. Wait, let's move this homework because that's not going to be done for a while. Okay, now propanal. All right, that's pretty easy. But here we go. Okay, so this we see an aldehyde. 1, 2, 3, 4, 5. This is the longest chain we can make because otherwise 1, 2, 3, 4. So you have to do then, and this has to be 1, so you can't go this way. So then 2-ethyl, 4-methyl, pentanal. Okay. Wait, where's my phone? Let me keep the chat open. All right. For cyclic aldehydes, in which the CHO, wow, interesting. Okay. So wait, let me first get the big example. So yeah, C double bond O H and C C C C C 1, 2, 3, 4, 5. So this one is going to be carbon 1. So then 1, 2, 3, 4, 5. This is going to be 2-ethyl 4-methyl pent now. All right, so now for cyclic al's where CHO group directly on ring, the name is the ring plus carbaldehyde. So what does that mean? That means if we had cyclohexane with connected to a CHO group, this would be cyclohex and carbaldehyde. Bro, what the hell? Two naphthalene carbaldehyde. Why does this have to be carbon 1? Acrolein. Now Red made that. It's too hot out here. Propanol. Oh, really? So wait, propanol would be C C C double bond O H, which would be, and this is called acrolein. I think this stuff is like super nasty, but it's actually called propanol. But I think that stuff is super toxic. All right. Naming is pretty simple. Ketones are named by replacing the terminal E with "-one". The parent chain is the longest one that includes hold on. Let me focus. All right, we're talking about ketones now. So ketones are named by replacing the terminal E of the corresponding alkane with the name "-one". The parent chain is the longest one that includes the ketone group, and the numbering begins at the end nearer the carbonyl carbon. Okay, makes sense. All right, so ketone is -E to -ONE, and C1 at closer to the double bond O. Okay. Yeah, so 1, 2, 3, 4, 5, 6. This would be C1, and this would be hexan 3-one, or 3-hexanone. Okay, that makes sense. Okay, this is a good one. 2-one, 1, 2, 3, 4, 5, 6. Okay, so it's gonna be hex. So wait, this one, let me draw it out. Okay, so C4, 1, 2, 3, 4 has a double bond. And then C2 has the own group. So this is going to be hex 4N 2-one, or 4-hexene 2-one. Okay. Oh, interesting. Okay, yeah. Okay, so you can also do, let's get another one. 3, 6. Wait, let me draw it bigger. Okay, so we have a own here and an own here. So this would be hexan 2,4-dione. Hexan 2,4-dione. Okay. A few ketones have allowed to make. Okay, so a few common ketone names that are non-systematic. Acetone, acetophenone, phenone, okay, which is just acetone connected to a benzyl, a phenyl ring, and then benzophenone, acetophenone, and benzophenone. Didn't we make this in lab? I think we did. This one is benzophenone. When it's necessary to refer to the RC as a substituent, okay. When it's necessary for the RC double bond O group as a substituent, the name acyl is used, and then ending "il" is encoded. Oh, geez. Okay. When we need to have the RC double bond O group as a substituent, it's named an acyl group with ending "il." So dash COCH3 is acetyl group. CHO is formyl. That one's weird because that one's not even a ketone. And then COAR is air oil. So CO phenyl is benzoyl. If other functional groups are present, and the double bonded oxygen is considered a substituent on a parent chain, the prefix oxo is used. Really? Wait, can I also call this hexane 3-oxo? Okay, that's niche. All right, so we have also if we have multiple substituents. So let's 1, 2, 4, 5, 6. This is an aldehyde on 1, and then on 3, this is also like this. This is called 3-oxo hexanal. Hexan 3-oxo. Why does the aldehyde get preference, I guess? That's kind of the interesting thing. Alright, so we're going to do all the problems, right? Alright, so 1, 2, 3, 4, 5. So, all right. So it's gonna be 2-methyl pent 3-O. Okay, I'll be right back. Let me get some coffee. Yeah, it is. No, you're good. Oh, okay. Aim was canceled. Oh, that's okay. Good. Um, let me look at my calendar real quick and put you on speaker. All right. Yeah. So you said the 16th. Would it actually be possible to um go to like July 3rd or something? Yeah, so I can just send her a message then, like when the time, in a couple weeks or so. Okay, that's great because yeah, that'll be my finals week, and I'll be awesome. Thanks so much. Yeah, you too. Okay. Wait. I think that's fine, but I didn't mute it. Bro, it's so annoying. All right, that seemed fine. All right, no risk. Holy cow. All right, so let's get back to it. It's chemistry time. It's chemistry time. It's chemistry time. Let's do it. All right. Okay, so we got the first one, 19.2. Oh wait, this is B. A, B. All right, so this looks like, so it's an aldehyde. It's not directly connected to the ring. Hold on. I guess it is, right? So this would be, no, what? The CHO is not directly on the ring, so how do you name that? This isn't interesting. One, two, three, double bondo. So this, I have no idea how to name. So you would consider this thing is the phenyl, and then this you would call propanal. So propanal and a phenyl ring. How do you name? Okay, so it is literally just 3-phenyl propanal. Okay. Okay, here we go. We have a dione, which that should be fine, right? We can do dione. 1, 2, 3, 4, 5, 6, 7, 8. So this is on 1, 2. So wait. So it's octan dash 2 comma 3, 4, 5, 6, 2, 6 dione. Bro, I actually hate this search. This search sucks. It's like, why is it so bad? Like, mine sucks, but this one really sucks. What if I do 2, 6 dash octan dione? Bro, even that doesn't get it. What do you call it then? Let's duplicate this and go to the answers. Chapter 19. Wait, did I get the other one right? I must have. Three phenylpropanol, 2,6 octan dione. All right, so yeah, wait, but this is octane dione. But in any case, can I just like, okay. Yeah, I feel like, I don't know. Search is just an inherently hard problem, I think. So, okay, but that's the answer. So let's keep going. All right, this one, I think it's probably just going to be this is not carbon 1 anymore. And this is going to be this carbaldehyde. So it's going to be like methyl. I think it should just be. Oh, how do you number on this one? This one's kind of interesting. So first off, it's going to be. Okay, D is really pretty interesting. So let's draw this out. So we got the ring, the cyclohexane ring. Then we have a dash on the CHO. And then we have a wedge on the methyl. So I think that my intuition is 2-methyl, or trans, 2-methyl, cyclohexane, hexane carb aldehyde. That's my guess. All right, let's do all of them and then we'll circle back. But like, which gets C1? That's the main question. Is like, do we think I mean, presumably the aldehyde is this, or the carbon attached to the aldehyde is the C1, but why? Okay. Oh, this one's good. 1, 2, 3, 4, 5, 6. I think, wasn't this already an example? Didn't they do this earlier? This is going to be hex 4n then just al, hex 4n al. Or do we have to do some weird oxo thing? That would piss me off, actually. I think it's gonna be, it's either that or 4 hexene al. Yeah, those are probably both right. Okay, F. Alright, so we have a cyclohexane ring. We have a ketone on the ring. And then we have a 1,4. Again, what gets the C1? I would guess that it's going to be 2, 3, 4, 5. Wait. 1, 2, 3, 4, 5, 6. Okay, so this is going to be 2, 5. So I'm going to say 2, 5 dimethyl cyclohexanone. That's going to be my guess. So let's check my answers. Okay, so C was octane 2,6-dione. This is trans 2-methyl cyclohexane. I always forget the E here. Hexane carbaldehyde. Okay, then 4 hexene al. So let me just do this. Okay. Okay, and then, oh wait, I forgot the cis. I need the cis. So cis 2,5-dimethyl cyclohexanone. That one's pretty easy. Okay, draw the structures now. 3-methylbutanol. 3-methylbutanol. Why did I have my lung? Okay. 2, 3, 4. Double bond O. 1, 2, 3, methyl. Alright, that one's pretty easy. 4-chloro-2-pentanone. 2, 3, 4, 5. Double bond O on 2. 1, 2, 3, 4. Cl, that one's pretty easy. Phenylacetaldehyde. So acetaldehyde is ethanol. So that's just this. Wait, actually, I don't think this is right. Alright, I think it's that. Alright, that one's pretty easy. Alright, cis 3. Oh, whoa. Alright, cis 3 tert butyl. Cis 3 tert butyl cyclohexane carbaldehyde. So what that means is that the T-butyl and the carbaldehyde are cis to each other. Okay, so first, the main thing is first you just draw the cyclohexane. Okay, then we're going to put the CHO group on here. So it's just going to be like this. So this is going to be C1. So then 2, 3. Here, and this should be a wedge. So we'll make this a wedge. So then we want to make this a wedge. And this is just what, methyl? No, this is T-but. So it'll be C, CH3, 3. Alright, that one's actually pretty easy. Cis 3 tert butyl cyclohexane carbaldehyde. 3-methyl butanol. Okay, so but, so 2, 3, 4. Double bond O on the end. 1, 2, 3. Double bond. And this is a methyl. 3-methyl 3-butanol. Okay, I got it. That one's easy. Alright, last one. Ooh, I love these nested ones because these ones get weird. 2,1-chloroethyl 5-methyl heptanol. Alright, so first we need 2, 3, 4, 5, 6, 7. Heptanol, so we put the double bond O on the end. Then we have 5-methyl, 1, 2, 3, 4, 5 methyl. Then 2, 1, 2. And then a chloro. Alright, let's check the answers. Okay, that's right. That's right. Uh, that's right. That is right. Um, that is right. And that is right. All right, those are pretty easy. I mean, naming is always the easiest part, like to like conceptually get, I think. Preparing aldehydes and ketones. Preparing aldehydes. Perhaps the best Perhaps the best method of aldehyde synthesis is by oxidation of a primary alcohol, as we saw in chapter 17. The reaction is usually by DMP, des-Martin periodinane, in DCM. Okay, so let's just say okay, des-Martin. Does it have wait, when I look up uh it doesn't have the DCM listed, but like how important is that? I don't know. All right. Another method of aldehyde synthesis is one that we'll mention here just briefly and then return to in chapter 21. Certain carboxylic acid derivatives can be partially reduced to yield aldehydes. Oh, interesting. Cool. The partial reduction of an ester by diisobutyl aluminum hydride. Okay, is an important laboratory scale method of aldehyde synthesis, and mechanistically related processes also occur in biological pathways. The reaction is normally carried out, dry ice temperatures and toluene. Oh, wow. Okay. So let's write that down. That's a crazy reaction. Okay, so is it specifically esters or is it just like okay. So mainly esters, but also other um, derivatives um, can undergo partial reduction to aldehyde with reagent dibal H, which is diisobutyl aluminum hydride. Okay, so for an example, we have this methyl s. Yeah, um, methyl ester. Have we named esters yet? I don't think we named esters yet. So anyway, so the thing is ester. So let's just say R C double bond O R prime, and then the reaction arrow is one dibol H two, or in toluene at minus 78 C, and the second thing is acid. Yeah. And that gives us the aldehyde R. All right. So we get the aldehyde. Okay. Okay. How would you prepare pentanal from the starting material? 1, 2, 3, 4, 5. DMP, Des Martin periodinane. Because this is pentanol. And pentanol oxidized is a primary alcohol, and you can oxidize it with Des Martin periodinane to form an aldehyde. So that is pentanal. Okay, here we have pentene, or one pentene. Wait, 1, 2, 3, 4, 5. Oh, 6. We have one hexene. Let me think about that. Wait, what? That's not hexene? Bruh. That's the most annoying thing. We gotta fix that, dude. It's so annoying. Um, so there's that. But then what about yeah, it's probably just this. Let me just add, okay, let me go back to the codex. Okay. Um okay, it's very frustrating to always search up the starting molecule and then say, "Oh, we can't find it." Go to PubChem and find and paste in the CID. Isn't there just a PubChem API that we can use for our search so that we can select what we want? Because it's really annoying to always have to go to PubChem. Also, one thing that I would like is I just did the reaction of one hexene and then did ozonolysis. And okay, well first just handle the search thing. Well, you can handle the other stuff later. But it's really annoying to have to go to PubChem. All right, let's see if we can fix this. But it's not even that. It's that one hexene didn't even work. Now this is going to be interesting because, like, let's say that how do I reduce? Yeah, so okay, so it's definitely I would consider it a bug that this is not, because if I for instance had penta now and then I did LAH. Wait. Ooh, that's a good idea. Okay, so wait, so the fixes are reducing aldehyde with NABH4 or LAH not working. And the second thing is how to handle I think the best way to handle something like that produces mixture, like an alkene ozonolysis. Because what if we had two, wait, three hexene? Oh, wait, bro, see, that's pissing me off. So I think the simplest option is that in the event if the code sees that the product is two things or more than one thing, then you just pick. You just assume, okay, we could like distill it and something like that. All right, so let's just get this fix in because this is driving me freaking crazy. Okay, I don't know how long the updates take. Okay, give it a second. Is it live? Yeah, we got the. Okay, cool. Okay, wait. So let's try it out. So one hexene. Bro, what? Okay, but literally. Okay, so three issues. Uh, when I typed in the number one dash hexene, nothing came up. But when I did one space hexene, it got it. But I don't know why. But for the first case, why didn't I get a list of the PubChem suggestions or anything like that? And of course, I would limit the number of them to probably only the top few. Okay, but that's one issue. Just we need to make sure that the search is at least semi-functional, or at the very least, when it says input a smiles or a CID, the CID could be a link that just like have a link there that sends you that at least allows you to click and open up PubChem to search for it. Okay, that's the first thing. The second thing is I noticed that using lithium aluminum hydride or sodium borohydride to reduce an aldehyde, it wasn't working. So obviously we need to fix. And I didn't test ketone, but I'm assuming that ketone reduction with those reagents also didn't work. And then also, I tried doing ozonolysis on a reagent, and the thing that was shown was an SVG of actually like fragments all together, which was actually pretty cool to see. But I think that points to the problem is now that we have this graph that is not fully or not is has multiple connected components that the second that you try to then, or at least, okay, I had some molecule. I think it was a terminal alkene. Then I did ozonolysis, and I got the resulting thing was was two fragments. Then I tried to do something on it, and I don't think it worked. So I think the broader point that I want to focus on is in the event that there are multiple products from one of these things, I think the hot path that really should be supported is that it says, okay, there are these multiple, which one do you want to proceed with? Because that's kind of, in synthesis, that's kind of all you care about is taking this one path. And so the fact that there are others you can kind of drop, though it's useful to know. So those are the three things to get working. I mean, how insane is that? So if I type in, what about hex? Like, why is it all caps though? Like, I don't really get how these names get generated. Okay. Anyways, the answer here is DMP. The answer here is just going to be ozonolysis, or I think hot KMNO4. Although, does hot KMNO4 on a terminal alkene? Yeah, that's what I thought. Yeah, the fact that it doesn't get CO2 there, I'm like not. I'm not crazy concerned with that. I mean, it's definitely a correctness issue, but I'm not like so upset about that. Okay, here we have a methyl ester actually. So this is 1, 2, 3, 4, 5, 6. So 2, 3, 4, 5. Double bond O O methyl. So here, this is that reaction of dibol H in toluene at minus 78, and step 2 is H3O. And this gives us pentanal. So this is C, D. One, two, three, four, five. I think this one's pretty easy. So we start with a 1 pentene. Okay, let's see if we can do it here. So I think that besides the reduction part, so we get, bro. Okay. So first it's BH3, H2O2, NaOH. Then 2 is DMP. All right, let's see. Did we get the? All right, so let's try this again. All right, thank God. Okay, wait. So wait, but now I want to do okay, so we have hexene. Bro, why does hexene default to um can we try that again? I want to see exactly what just happened. Okay, so 1 hexene O3. I mean, that's pretty good. That works for me. Okay, but now we need to check the does oh, because this is different. Wait. There's this, but this is for um this is for doing a Markovnikov addition without um carbocation. But that's not what I want. Um I'm noticing that so I have pentanal, which means, the pentane aldehyde. And I tried to type into the reagent search bar NaBH4, and the only thing that seemed to come up was well, it said no product rule, but it came up with the oxymercuration demercuration stuff. So for some reason that reduction is not in or something. The LAH seemed to work though. So wait, let's try it again. Pentanol. Or wait, no, pentanal. Um, LAH. Oh wait, really? Yeah, because it's like or, but then the search didn't do. That's pretty dumb. The search definitely seems better though. Uh, so we did them all, right? What is CrO3? Wait, what is CrO3? Oh, let's see, can we look at the actual? Because I want the arrows to be like pretty good. So if I have if I have pentene, and then I do BH3. Oh, so it does at least have this, which is nice. I think it should be more visible here, but it's like close enough, right? Okay, but that's good. All right, so it said it pushed. So let's just try to get a pardon me, alcohol. Oh, because I'm wrong. Oh, wait. Oh, I mean, okay, that's fine. All right. Yeah. Wait. So let me try to do this again. No, but wait. But I'm definitely seeing it on this computer. Penta now. NABH4. What? But it's working on my phone. I hate when you do something to Codex, you tell Codex something and you were wrong, and then it does a bunch of stuff. That bothers me. Oh, what's up? I gotta fix it. It's not working. Okay, so the commit pushed. Alright, do we have a new one? Penta now. NABH4. Okay, there we go. Alright. It works. But I don't like this. But okay, that's. I mean, at least it works now. So let's keep going because there's a bunch of sections left to do. Okay, but all these problems are pretty much handled, I think. Let's see, 1, 2, 3, 4, 5. Yeah, so pentanol. Okay, so that one works. This is 1, 2, 3, 4, 5, 6. And this is going to be O3. And we want this fragment. And then we're good. That one works. Then here we have... Oh, this is going to be interesting to see the input for. So this is going to be... How do you name this? Let's see. Alright, let's see if methylpentanoate works. Methylpentanoate. Oh, wow. That's sick. Okay, so now we want diba. Okay, more broadly, there are a few things that should probably be consistent. In a few places, I really like for instance, hydroboration to make an anti-Markovnikov alcohol, it actually shows 1 BH3, 2 H2O2 NaOH. And I really like that for all of the pathways, for all of the transformations that we do, I think it's important that we have the content that we as students should put on the arrows on our exams, because that's the important information. So that's the more general thing that maybe a cleanup needs to happen to make some consistency there. The second thing is there is a reagent that for our purposes all we have to look for is esters, but it's called Dibal, DIBAL-H, and you can look up the reagent info, but I think what my book says is that the first step is this Dibal-H thing. It's in toluene, and it's at minus 78 C. And then the second step is acid. And basically what this does is, again, it produces fragments that need to be chosen from, but it gives you an aldehyde by breaking off the ester. So that's a reagent that needs to be handled. All right, let's keep it going. Let's keep it going. So, but I really like the new search is much better, which makes me happy because I don't know, search is just really weird. All right, so let's get the Dibal-H in. And then this one, so this one we didn't, this one is easy because it's just 2 steps. So this is pentene. So where is my chemical? So pentene, BH3, DMP. Bro, look, this app is so sick. I love chem rules, bro. It's so much better than all the other ones. Like, OrgoSolver is so fucking slow. This one, you can hammer the reactions. Just bam, bam, bam. Alright, preparing ketones. For the most part, methods of ketone synthesis are similar to those for aldehydes. Secondary alcohols are oxidized by a variety of reagents to give ketones. The choice of oxidant depends on the factors such as reaction scale, cost, and acid or basic sensitivity of the alcohol. DMP is common, and chromic acid. Other methods of include ozonolysis of alkenes. Ozonolysis of alkenes in which one of the unsaturated carbon atoms is this. Wait, hold on. Ozonolysis of alkenes in which one of the unsaturated carbon's atoms is disubstituted. Does that work? So if we had, what would this be called? 1,1-dimethyl. Or actually, no, it would be 1, 2, 3. It would be 2-methyl. Oh, wait. Oh, actually, wait. Would it be 1-methyl, 1-ethene? Would a... How to name something with... it's ethene, but one side has 2 methyls. Is it 1-methyl, 1-ethene? Or wait, no, 1-propene? Or 2-propene? Two methyl. Oh, yeah, 2-methyl prop 1-ene. Let's see. There's no way this name works. Oh, that's lit. Holy shit, that's lit. All right, and so now we react it with O3. So this, interesting. Okay, wait, let's test the diball thing. So wait, what does diball do? Diball takes something like methyl pentanoate and wait, what? Are we in the wrong commit? Bro, what? I feel like there's a caching issue. I feel like there's a caching issue on Firefox. Like, am I crazy? Because, like, watch, on my phone... Okay, so methyl pentanoate. Okay, loads. Diball. Oh, and the fragment thing worked? That's so lit. Holy shit. I feel like I'm noticing more caching issues because on my phone, you know, okay, so I'm using my phone and my laptop. I verify that the commit hash is the same. I try to use Dibal, D-I-B-A-L, you know, the new reagent that we added. on my laptop and it doesn't find anything. But then I try on my phone and it does find it. I mean, is that just a Firefox issue? Like, I don't know. It's really annoying though, because it works on my phone and they're on the same commit hash. Okay, wait. I want to try the isobutylene thing. Okay, so we have isobutylene, and then I want O3, and I want to see if it gives me the picker. Okay. Oh, it does. Oh, that's so lit, dude. Holy cow. Wait, oh, okay, wait. So, no, you do this, and then you do this. Okay. All right. So that works. You can do that. All right. So that's good. That's good news. Um, I think I do need to learn this, but I don't know what this is about. Friedel Crafts acylation. It's adding an acyl group, which we just learned. An acyl group is wait, what is acyl group? Oh, an acyl group is just the substituent of the aldehyde, so it's just the RCHO thing, or not aldehyde necessarily, but like a carbonyl. Let me go to that. Dude, vibe coding is just the best, most addicting thing ever. You can just iterate so quickly, man. All right. In addition to those methods already discussed, ketones can also be prepared from certain carboxylic acid derivatives, just as aldehydes can. Among the most useful of this sort is between an acid chloride and a lithium diorganoreagent. Diorganocopper reagent. All right, that one's niche, but maybe I will. I mean, I guess I have to support them all. All right, so 3-hexyne. So 3-hexyne to 3-hexanone, which is I mean, so that works, you know. But is that the best way? That's the way I came up with. Let's do the wait. Oh, do we have this? Okay. Benzene to M bromoacetophenone. Okay, so I think that's so meta bromo. So wait, hold on. Because ortho meta para. Ortho meta para. So let's draw a benzene ring. Then acetophenone is going to be then meta bromo. So you're going to take benzene. Wait, is meta next to meta has? I always forget, but I think meta is. Yeah, meta is on the 3. I have no idea how you synthesize that. Yeah, so that's right. But then, bro, how do you do that reaction? I think that might be the Friedel-Crafts acylation. But still, okay. Okay, so I don't know if this has come up before because in SN2, I don't know exactly how the graph, how the rule engine finds SN2 products, but what I want to add now is Friedel-Crafts acylation. And I think the distinction here now is that you have a reagent set, but then you also have this acid chloride. And so, you know, there's an infinite number of these acid chlorides that you could provide. So, what is the mechanism that we should use to allow people to do Friedel-Crafts acylation? Um, because there's kind of like, you need to provide the aluminum chloride and heat thing on the arrow, which is just the actual what you'd consider the reagents, and then you need to provide the the acyl donor. So I don't really know how to do that. Also, did you go through all of the reagents and start to standardize, or at least place somewhere visible on the app? It doesn't have to be big, and really just minor modification to show what students should put on the arrows in exams. But Grignard is not really like. Oh, what's up, dude? I didn't see so many people. What? This is live. Yeah, I'm live. Gang, it's Ortho Meta. Yeah, that's what I thought. What's up? Your time to shine, Arcadius. I'm reading the chats, bro. I'm here. If you're still here, I'm here. Yeah, I haven't read the heterolytic. I don't know any of that stuff yet. I have to do that chapter next. What's up, Arcadius? Bro, have you been watching this app I've been building? That's what this whole thing is about, man. Okay, you got a secondary alcohol. You want to oxidize it? DMP. Boom. Ketone. Get on it. That's what's up, bro. That's what's up. This thing is so sick. Anyway, so that's like why I'm going slow, because I'm trying to implement all of these rules into my app. I mean, it's just a website. It's a free website. Anyone can use it. It's actually static. So it's like, bro, this is the best. It's fast. It's static. It's just like, yo, it's so lit. Totally free, no accounts, no bullshit. You just hop on and start synthesizing, bro. So that's what's up. So that's why I'm going slow, is because, like, for instance, I don't think I ever got this right. Let's try bromopropane. Yeah, fine. Bromopropane. Is it gonna do it? Okay, good. And then if we did magnesium, we get a Grignard reagent. And if we want to do something like formaldehyde, yeah, formaldehyde. See, it doesn't work yet. That's what I'm saying. I never fixed this. Yeah, so the Grignards don't really work. So this next commit that it's working on probably is not going to work. How to do the acylation? All right, I want to try let's get the acetylation. Wait, what should form what, the Grignard? Wait, the Grignard, what happens? You have this MgBr, and then you have formaldehyde. This comes in attacks. Doesn't it just form a... Doesn't it form an aldehyde? Oh wait, here it is. Wait, but does it reduce? Or does it just stay an aldehyde? Bromopropane with formaldehyde. So, okay, wait, yeah, so then you have this... Wait, I gotta remember the mechanism. I hate how ChatGPT does this. It's so hard to read. Okay, yeah. I want to add mechanisms to my app, but it's going to be way more work. Oh, you can do Grignard on epoxide too? Oh, yeah, I didn't even realize that. That's cool. Okay, but where's just the general? Okay, here we go. But where's the? Okay, here we go. Oh yeah, it pops onto this. Oh, and that's it. Okay. So yeah, so then this comes up here, and then on. So this is on one, and then two. H plus this text this two. Okay. All right. That makes sense. Okay, wait. It said it's done. Let's see how we can do this Friedel Crafts thing. Oh, for substituted aromatics. Yeah, we got to do the regiochemistry stuff. I haven't, yeah. All right, so we can test it with benzene. All right, so let's do this. Benzene, AlCl3. There's no way this works. AlCl3. Yeah, there was no way. I think. Yeah, no suitable. Or the acid chloride could not be parsed. Yeah, I mean, okay. So, I gotta keep going, but that is something that we definitely gotta fix, because that's annoying. Okay. So how the hell do we form this stuff? Benzene. So I know how to do the acylation. So first you can find acetophenone, but then how do you get meta? So the okay, good. Oh, okay. So yeah, I just haven't learned that yet. I don't know why our class they're teaching this before. Dude, like the order in which we learned these chapters was nuts. Like all over the place. Makes no sense, but whatever. Okay, oxidation of aldehydes and ketones. Aldehydes are easily oxidized to yield carboxylic acids, but ketones are generally inert towards oxidation. The difference is a consequence of structure. Aldehydes have a CH, or an H proton that can be abstracted during oxidation, but ketones do not. Many oxidizing agents, like basic KMNO4 and hot nitric acid, convert aldehydes into carboxylic acid. Okay, so let's take an aldehyde and add. Okay, so okay, I'm noticing that potassium permanganate does not work to turn aldehydes into carboxylic acids. Okay. Aldehyde oxidations occur through intermediate 1,1-diols. Wait, hold on. Okay, you get meta when you react acetophenone with bromine gas. Maybe you need the presence of water. Wait, for what? It's hard for me to track. So wait, let's see if okay. So this thing is not gonna. Dude, I gotta like rewrite this whole thing. Like it's like pretty dumb. Okay, ketones are inert to most oxidizing agents, but undergo slow cleavage of the CC bond next to the carbonyl. Hexane dioic acid? Yeah, I've never. That's crazy. Cyclohexanone to hexane dioic acid? Don't you need to number these? Shouldn't it be like 1,6 hexane dioic acid? I'm not going to implement that rule. That rule sounds niche, bro. Water is when phenol or aniline. Okay, nucleophilic addition reactions of aldehydes and ketones. The most general reaction of aldehydes and ketones is the nucleophilic addition reaction. Alright, so I'm going to have to do this mechanism. A nucleophile approaches the carbonyl. Wow, it's like the fact that they know this is crazy. An angle of 105 degrees opposite the carbonyl oxygen and forms a bond to the electrophilic CO carbon atom. At the same time, the rehybridization of the carbonyl carbon from sp2 to sp3 occurs. An electron pair moves towards the electronegative oxygen, and a tetrahedral alkoxide ion intermediate is produced. Protonation of the dude, it's actually crazy that like all that makes sense to me. These words, like a few months ago, I mean, you'd just be like, what the hell are you talking about? But now it's like, oh, that all makes sense. That's cool. Protonation of the alkoxide by addition of yeah, it gives you that. Okay. All right, so let's just draw this mechanism. So we have a ketone. All right, then the nucleophile comes in and pushes the lone pair onto oxygen, and then on. So this is on 1, and then on 2, this lone pair takes. Fun. The nucleophile can either be negatively charged or neutral. If it's neutral, it usually carries a hydrogen atom that's be subsequently eliminated. Okay. Nucleophilic additions to aldehydes and ketones have 2 general variations. Oh, what? Oh, that's interesting. Okay, so there's 2 kind of ways you can do this thing. You have this ketone, and so this is like the first way, And nucleophile with that's negatively charged comes in, pushes that lone pair on, and then, then you have, so that takes this to single bonded but tetrahedral. And then HA, we have some acid, and this is minus, and this attacks this proton. And then you get alcohol. The second way is weird. You still start off with this ketone. Then a protonated nucleophile comes in. And it has a lone pair, I guess. Comes in. It still pushes the lone pair onto oxygen, so that's minus. And the nucleophile is positively charged. Then this attaches to that. So this, I guess, pulls off one of these. Or it's just like a hydride shift type of thing. And Isaiah's probably talking about this bottom one. I think this bottom one is weird. And then what causes the removal of the water, though? Okay, so these ones kind of do the normal top half, and then these ones, so alcohols, yeah, nitrogen, this really seems like a nitrogen compound thing, but I guess water too. The interesting thing about water is that if this is oxygen, then you actually end up with the same thing as you started with, because you end up with the same ketone. So for water, this bottom pathway is identical to the starting product. But if it's an alcohol, what happens if it's an alcohol? That's interesting. Because now you have an R here. So presumably this is an R. Tetrahedral enemies. It protonates and becomes a good leaving group. At the same time, OH protonates and becomes a good leaving group. It's very hard to keep track of chat and do this, because what is it? It protonates. What is it? Is it this? Becomes a good leaving group? Or is it this protonates and becomes a good leaving group? It's probably this. Because, yeah, no, it's got to be this. Protonates becomes oxonium. Wait. I don't know. I gotta keep reading. Aldehydes are generally more reactive than ketones in nucleophilic addition reactions for both steric and electronic reasons. Okay, that makes sense. Sterically, the presence of only one large substituent bonded to COO in an aldehyde versus two large substituents in a ketone means that the nucleophile is able to approach easily. Okay, yeah. The transition state leading to tetra is less crowded. Okay, that's obvious. Okay, so let me just write it in my notes at least. Yeah, that makes sense because otherwise, obviously, OH is not a good leaving group. All right, aldehyde more likely to do SN2 more reactive, or not SN2, just nucleophilic substitution. Reactive because sterics, obviously. That's an easy answer. But was the electronically aldehydes are more reactive than ketones because of the greater polarization of the aldehyde carbonyl group? To see that, it's probably because the higher substituent count is like there's more electron donating groups, right? To see this polarity difference, we call it the stability order of carbocations. Yeah, exactly. Yeah, makes sense. Okay, so and electronically, ketones have more EDG on carbonyl carbon. All right, so more electron donating groups. That's also pretty obvious. In the same way, an aldehyde only has one alkyl group and so also you could think of that's why probably formaldehyde is great. Is pretty reactive. In the same way, an aldehyde only has one alkyl group inductively stabilizing the partial positive charge on the carbonyl carbon, and is a bit more electrophilic. One further comparison. Aromatic aldehydes such as benzaldehyde are less reactive in nucleophilic addition reactions than aliphatic aldehydes. Because the electron donating resonance effect of the aromatic ring makes the carbonyl group less electrophilic. What does aliphatic mean again? Oh, okay. Yeah, exactly. Yeah. Where are we at here? Oh yeah, and then aromatic carbonyls less likely to substitute because resonance from phenol. Treatment of an aldehyde or a ketone with cyanide. Followed by protonation of the tetrahedral alkoxide intermediate gives a cyanohydrin. Show the structure of the cyanohydrin obtained from cyclohexanone. Alright, so let's draw cyclohexanone. and it's I mean structurally, but whatever. So C triple bond N minus. I always forget which. Okay. Is it the nitrogen attacking or the carbon attacking? I guess it's the carbon attacking. All right, so it's probably just So is it not just wait? Let me just do we have it in here? 19.5. Oh yeah. Wait. Yeah, that's it. Okay, that's not that exciting. P-nitrobenzaldehyde. So para-nitrobenzaldehyde. All right, let me draw that. 19.6. Para-nitro. Benzyl. Okay, so phenyl ring, then the CHO group, and then para to that is going to be NO2. If you oxidize it, you get a carboxylic acid. Interesting. Para-nitrobenzaldehyde is more reactive than para-methoxybenzaldehyde. More in nucleophilic addition reactivity than paramethoxy. So this is MEO. So that's like an ester group. Or not ester, ether group. And then this. Why would it be more reactive? Wouldn't you expect it to be less reactive? Because way more resonance happens there. Because my understanding of this section was that aromatic are less reactive in it because I gotta look it up. Actually, wait. I have the student manual or on the website you can get the student manual. This thing is actually really good. 19.6. Oh, I see. I assume because greater resonance, but the fact is that nitro group is very electronegative. I see. Okay. Right, so it pulls the density. Okay, that's fine. I get it. And here it's just not that much. Oh, also, guys, I really want to implement. I don't even know how I'm gonna do this, but I want to implement like proteins as reagents. Cause like, obviously, what are the best reagents? What are the best? Like, the best reagents are all proteins. Like the fact that we just have proteins at all is it really is insane. Like, chemists, like, organic chemists, all their reagents are these nasty, disgusting, like, oh, this will kill you, that'll kill you. But biochemists are like, we just make a protein for that. And it's like not dangerous. I don't know, there probably are dangerous proteins, but I guess there are dangerous proteins too. So I retract my statement. But it's different. All right, yeah, I wanted to see this water one. Aldehydes and ketones react with water to form. Oh wow, geminal diol. Really? Geminal diol? Well, I mean, I would have. I'm not saying that organic chemistry is worse than biochem. I'm just saying, like, uh, the generality of proteins is unbeatable. I mean, yeah. And a geminal diol can eliminate water. All right, so yeah, I'll write this down. So we have acetone plus water, and this does this whole thing of it comes in, pushes this, and then so this is on one, on two, and this gives us um, OH and OH, the geminal diol. But this is like 0.1%, and this is 99.9%. Okay. The position of the equilibrium between a geminal diol and an aldehyde or ketone depends on the structure of the carbonyl compound. Equilibrium generally favors the carbonyl compound for steric reasons, but the gen diol is favored for a few simple aldehydes. For example, an aqueous solution of formaldehyde consists... Wait, really? Wait, is that true? That's so weird. Alright, bye, Arcadius. Wait, Arcadius, where are you from? Where are you at right now? It's 1 a.m.? That's 12-hour difference. Okay, formaldehyde? Dude, that's wild. This is 0.1%, but this... It's called the formaldehyde hydrate. Is 99.9%. Why? Alpha keto carboxylic acid. Oh, alpha keto carboxylic acid. Okay, that makes sense. This is the alpha carbon of the carboxylic acid. And it's a keto group, which have adjacent positively charged carbons. Okay, so hydrate. which have an adjacent positively charged carbons that destabilize the keto form in favor of the hydrate. Such compounds occur commonly in many biological pathways. Pyruvic acid, which is 60% hydrated equilibrium, and alpha ketogluteric acid, 50%. Okay. Under basic conditions, the nucleophile is negatively charged and uses a pair of its electrons to form a bond to the electrophilic carbonyl carbon. At the same time, the carbonyl carbon rehybridizes from sp2 to sp3, and two electrons from the carbonyl pi are pushed onto the oxygen, giving alkoxide. They're just repeating the same thing. Protonation of alkoxide uses neutral addition. Wait, plus regenerated? Oh, yeah. Under acidic conditions, the carbonyl oxygen is first protonated by H3O to make carbonyl. Oh, yes. Okay, yes. So the protonation of the carbonyl oxygen makes the carbonyl carbon even more electrophilic. So then a neutral molecule like water, okay, yeah, can then use its electrons to come in. All right. Interesting. It's kind of like two sides of the same coin. Um, Two electrons from the carbonyl pi move onto the oxygen. It's just kind of the order of operations, huh? The positive charge on oxygen is thereby neutralized while the nucleophile gains a positive charge. Finally, deprotonation by water gives the neutral addition product and regenerates the acid catalyst. I still want to know, like, why is formaldehyde so favored? Or why is the formaldehyde hydrate so favored? Yeah, they're like opposites. I agree. Formaldehyde is tiny and very electrophilic. Oh, okay, but it sells as sterics. I mean, like, without the there's no yeah. Okay. Yeah, so it's both. Okay. That's pretty cool. Note the key difference between the base catalyzed and acid catalyzed reactions. The base catalyzed reaction takes place rapidly because water is converted into hydroxide ion, a much better nucleophile. The acid catalyzed reaction takes place rapidly because the carbonyl compound is converted by protonation into a much better electrophile. Okay, all right. Yeah, that's an interesting way to put it. Okay, so what did I just read? The addition of water to aldehyde and ketone, base and or acid catalyzed. So in one case, let's just draw our ketone. We have an OH, so this is basic. This is minus, and we have these electrons, and it comes in, and then, but what happens after is that just water, yeah. Okay. But in the acidic case, you have this ketone and H3O plus protonates it. So then what deprotonates the water? Water just takes it, right? Yeah. All right, that one's pretty nice. I like that. Damn, has it really already been 4 hours? No, okay, yeah. For some, that was. Damn, is this homework really due tonight? Is the homework hard? Do I have to? Let me look at it. Bro, okay. Can you just reduce it and then add ozonolysis? Or can you do ozonolysis directly on an alkyne? I don't know. Something like that though. This is definitely ozonolysis, bro. Oh, it's long. What the hell? I didn't realize this was so long. Wait, do I have to fill this out? You don't have to fill this out, right? Alright, I'll probably get this. I don't know anything about protection of ketone. Wait, what is Wittig again? Wittig is weird as hell, dude. Wittig is that four-member ring thing, right? Produce reagent to prepare the following compound but by Wittig. Oh boy. Okay. You probably just oxidize it and then you oxidize to a ketone and then you it's probably something like that. Grignard wait, Grignard detects a ketone. Yeah, dude, bro, that one's easy. What the hell? Uh Can you do this? Is this just this attacks this and then this comes into the carbon? I probably it's just that. Okay. 2 moles of ethoxide. I don't know this one. Wow, that one looks weird. That one looks weird. I don't know how that one works. And then this looks like an E2. What? What is going on with that one? Benzaldehyde. Does this not just form? Oh wait, does this form trimethyl or triphenyl methanol? This might be just form triphenyl methanol with the double. Can we do this in lab? I feel like we did this in because this is benzaldehyde. Dude, we did this in lab. I'm leaving. Oh my god, bro. I'm leaving. Does a strong base? This is probably a trick question in that a strong base messes with the ketone, or is it literally just add this NaNH2 at Br? I don't know. What? How do you do this? That one's weird. This one, I have no idea how you're supposed to do this. Actually, all of these. I really don't know how to do many of these. Okay, so we just learned this one. But often this side is favored. Oh, okay. So you can do a geminal diether. Geminal diether. Okay, that in acid. Okay, that's cool. What the fuck is that? This is this. What is this called again? All right, that one's weird. Okay, so this is that second route of the addition reactions that we were looking at. This is the second route where the nucleophile gets a double bond and it removes the water. That makes sense. What is NH2OH called? I've never even heard of that, dude. Hydroxylamine. That's cool. I've never even thought about that before. Hydroxylamine. It's a precursor to nylon. Interesting. Hydroxylamine. Interesting. Okay. Okay, yeah. So in basic conditions, 1 and 2. That's pretty easy. Is hydrate synonymous with geminal diol? I don't know. And then acidic conditions, yeah, this becomes more electrophilic. Water can come in, and then another water deprotonates. All right, so they're like the same. That's pretty cool, actually. That's pretty neat. That like the opposite conditions produce the same result. Chili. Dissolved in water. Trichloroacetaldehyde. Acetaldehyde. What is trichloroacetaldehyde? What? Oh. Is it not just... Wait, where's my... But here's the mechanism. See, that's what I wanted to see. Even though it's not a really basic environment, it's got to do this thing. And then... Oh, actually, yeah, this could just pull it from this one. Oh, yeah, that's right. That's what happened. Okay. So, all right. So it's... All right. Wait, let me get my phone. The oxygen in water is primarily oxygen 16. But water enriched with the heavy isotope oxygen 18 is also available. When an aldehyde or ketone is dissolved in oxygen 18, the isotopic label... Bro, I don't know how to explain that. What do the neutrons do? What the freak? But this doesn't explain why preferentially it would... Okay, I'm not even going to bother with that. That's weird. cyano. Aldehydes and unhindered ketones undergo a nucleophilic addition reaction with HCN to yield cyanohydrins. So cyanohydrin is RCH OH C triple bond N. So R. All right, so unhindered ketones and aldehydes. It's reversible and base catalyzed. Reaction occurs slowly when pure. What is this called? Is this just called? Wait, what is HCN called? Hydrogen cyanide. Or hydrocyanic acid. All right. All right, that makes sense. So, all right, cyanohydrin formation is somewhat unusual because it is one of the few examples of the addition of a protic acid. It's one of the few examples of the addition of a protic acid to a carbonyl group. As noted in the previous section, protic acids like water, hydrobromic acid, hydrochloric acid, sulfuric acid don't normally yield carbonyl addition products because the equilibrium constants are unfavorable. However, equilibrium favors the cyanohydrin adduct. Cyanohydrin formation is useful because of the further chemistry that can be carried out on the product. For example, a nitrile. Okay, so hold on. Can be reduced with LAH. Oh, interesting. to yield a primary amine. Thus, cyanohydrin formation provides a method for transforming an aldehyde or ketone into a different functional group. Oh, I see. Alright, let's draw this reaction. Benzaldehyde, HCN. We just drew what that makes, so we know that that's going to make OHCN. Okay. Then we have two pathways. We can do this, which is LAH in THF is 1. With water is 2. I don't know what's up with the water, but that's whatever. Phenyl here. So LAH reduces it so that we have... Oh. Yeah, so first you make this, and then you can make CNH2. That's pretty cool. Oh wow, I'd like to see the mechanism for that. That's weird. So then you have C double bond O OH. Cyclohexanone forms a cyanohydrin in good yield, but 2,2,6-trimethylcyclohexanone does not. Okay, so 2,2,6-trimethyl. So 2,2,6. So 1, 2, 3, 4, 5, 6. My guess would be sterics, but I don't know. It's got to be sterics. Yeah. Does Okay, so at least that works. Okay, nucleophilic addition of hydride and Grignard reagents. Okay, addition of hydride reagents. Reduction. We saw in chapter 17 that the most common method for preparing alcohols, both in the lab and in living organisms, is by the reduction of carbonyls. Aldehydes are reduced with sodium borohydride to give primary alcohols and ketones for secondary. Yeah. Carbonyl reduction occurs through a typical nucleophilic addition mechanism under basic conditions, as shown earlier. Although the details of carbonyl group reductions are complex, LAH and sodium borohydride act as if they were donors of the hydride ion. Okay. Not actually what happens, but that's kind of what happens. Yeah, so it's a lot like the um no, it's a lot like this. Okay. Um okay, 19.8. Uh addition of amines. So imine and N-amine formation. I think I'm gonna make some food right now. I'm like pretty hungry. Hmm. So this forms the wait, what? Oh, right, because this is a primary. So this forms the imine. Okay. Hmm.
Mm.
All right, that makes sense. It's 3-pentanone. How do you name them though? I got the first one. Let me do the second one. I don't know how to name them, but I got them. I actually like that mechanism. The imine and enamine formation is pretty nice. Not bad, not bad. Imine formation is reversible. Show all the steps involved in the acid catalyzed reaction of an imine with water. Do you not just reverse all the arrows? Imine formation, right? So we have imine formation. So the first thing that happens is this thing takes a proton. Then the next thing that happens... Okay, this is actually kind of fun. Alright, so show ketone form acid cat imine. Alright, so we have imine. And the first thing that happens is we have H3O. And this lone pair on the thing takes this. And we get N plus HR. And then water attacks, right? Yes. Okay, so this is done. So we're here now. Except for the H2O takes a proton. Okay, so now we have the alcohol. Is this called the carbolamine or something? Carbinolamine. Yeah, I'm so tired right now. What the hell? Carbinolamine. Carbinolamine. Uh oh yeah, and then this lone pair takes this hydrogen. Okay, I got it. Doing it the reverse is actually pretty interesting. That was a good problem. I like that one a lot. Flip all the arrows. Dude, I gotta hurry up. I gotta do the problems. Okay, 5-member ring. Double bond. N is, or blue is N. So N. And then these are ethyl groups. So that's it. So how can you make it from a ketone? So if we had a, oh, so this is an enamine. So the reaction of psych pent anone, psych pentone plus diethyl amine. It gives the product. Is that right? Is that right? Yep. Yep, 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 yep. Ugh. Ugh. I need to walk around. I need to wake up. I'm so tired right now. The process is a useful and general method for converting an aldehyde or ketone into an alkane. Oh, interesting. Huh. Okay, so we get here. So I get this. Now what happens? So this is the standard. Up to here is standard. Then, uh, OH minus comes and takes. So then you take a proton off of the second one. Carbanion. Oh, it takes a proton. So this is the KOH. The KOH is doing this. Oh wow. So I liked. Okay, so I verified that if I start with my like alkyl halide, and then I specifically like bromoethane, and then I do, magnesium, so Mg, space, and then in the same reagent set, put my desired, like ketone or something to react to make my alcohol for Grignard reagent or reaction. But I also want the other way to work, where I first put in Mg, press enter, and apply the fact to make the Grignard reagent, and then after that, say something like, whatever, 3-pentanone or some ketone, and then do the Grignard. So I want to be able to do them separately and together. I actually prefer separately, but both, in any case, at least some of it works. And then I'm also not. So I also want to see the enamine candidates ranked, but I'm not getting any enamine formation at all. I started with 3-pentanone, and I reacted that with diethylamine, and it said no candidates or something like that. Let me try again. It said, all right, so I do. So I start with 3-pentanone. Okay, good. Then I react that ketone with diethylamine. And it says no enamine product. Okay, let me try with a. What about dimethylamine? Still none. I don't know. By the way, you shouldn't be doing any string stuff. It should always be on the graph. I mean, I feel like we've gone over this enough times. Maybe you need to make a note somewhere, but no strings. No strings. I mean, it's just so brittle. We've already seen it cause bugs over and over again. Ugh. This shit just doesn't work, bro. Well, this is weird. How did the Okay, that looks good. All right, I gotta do the homework, bro. I'm running so behind. How much more is there? Okay, holy cow. Wait, what? Is it not just palladium on carbon? Yeah, that's right. Okay, that's cool. I love this graph, dude. That's good stuff. It's actually a commutative diagram. I don't even know what that means. At one point, I feel like I thought I knew what that meant, but I don't even know what that means. What the hell is a commutative diagram? Nucleophilic addition of an alcohol. Okay, so acetyl, acetal. I don't know how you say it. Oh wait, this is a plus. Oh, okay, wait, there's more. So then another ROH comes in. Okay. Mm. Ethyl 1, 2, 3, 4 oxo pentanoate. Okay. Interesting. All right, wait, hold on. Man, I'm so sleepy, dude. Okay, time to lock in. It's time to lock back in, guys. Wake the hell up. Acetals are useful because they can act as protecting groups for aldehydes and ketones in the same way that trimethylsilyl ethers act as protecting groups for alcohols. As we saw previously, it sometimes happens that one functional group interferes with the intended chemistry elsewhere in a complex molecule. For example, if we wanted to reduce only the ester group of ethyl 4-oxopentanoate, the ketone would interfere. Treatment of the starting keto ester with LAH would reduce both the keto group and the ester group to give a diol product. By predicting the keto group as an acetal, however, the problem can be circumvented. Like other ethers, acetals are unreactive to bases, hydride reducing agents. Oh, yeah, that's right. Like other ethers. But they are cleaved by acid. Thus, we can accomplish the selective reduction of the ester group in ethyl by first converting the keto group to an acetal. Wait, what's up with this thing, bro? What? Oh, wow. Wait, how does that work? Oh, it uses the same? Holy cow, that's actually sick. Damn. Ethylene glycol, bro. I think I found a bug in trying to reduce esters with something like lithium aluminum hydride. I'm pretty sure that it doesn't it just because the rule right now I think is just treating it like a ketone, but I think something else happens. Can you look into it and fix it if it's wrong? There's actually a lot in this chapter. Oh boy. Okay. This is going to be nuts. That seems hard. But I want to go back to, yeah. Wait, what is hemiacetal? Oh. Show the structure of this acetal. You would get, so, O, O, Yeah, that's what I drew. Let's go. Show all the steps in the acid catalyzed formation of a cyclic acetyl. Wait, did I just push a fix? Oh no, it was just the ester thing. Okay. Um. Show all the steps in the acid catalyzed formation of a cyclic acetal. Okay. Shoot, we're gonna need this page before this. Or actually, I'll just go here. Okay. Yeah, it's good to review this. Okay, so the first thing is the HCl. The lone pair on the ketone attacks the proton. We get OH plus. Then presumably ROH comes in. Yep. So now we have the hemiacetal, right? Water takes off that thing. Alright, now we have the hemiacetal. OH and OR. Okay? And we also have plus H3O. Okay, what happens next? More HCl. Okay, then the lone pair on the alcohol comes and internally kicks off the water. Okay, but now here is where this is actually equal to, we have O. Identify the carbonyl compound and the alcohol that were used to prepare the following acetal. Identify the carbonyl compound and the alcohol that were used to prepare the following acetal. Alright, so here's the acetal. Wait. Yeah, so then this had a ketone on it. It was just methanol, right? Damn, there's a lot. There's a lot to study. Okay, illide. I totally forgot about this one. The Wittig. Aldehydes and ketones are converted into alkenes by means of a nucleophilic addition called the Wittig reaction. R2C minus P plus phenyl 3. Illid. Illide. Dude, I'm like capping out. I can't focus right now. Should I just try to do the homework? Because that's what needs to get done, and then I can study this more later. Okay, let's just try to name this thing. Okay, so we gotta just get working because I'm like falling asleep. So this is 1, 2, 3, 4, 5, 6. So 5 dibromo, 2 dimethyl pentanal. Uh, where's the homework? There we go. 1, 2, 3, 4, 5. 2, 2, 5, 5 tetramethyl cyclopentanone. 2. Draw the structure 2,4 dimethyl 1,3 pentanone. Okay, wait, what? Wait, what? Oh no, no, this is just 3 pentanone. Okay, so pentanone and then 2,4. All right, that's easy. Okay, 3. No, but it's not. It's cyclo. It's cyclo. No. Damn, I totally forgot this. What? Is this not just ozonolysis? Let's see. This is going to be methylcyclohexene. Wait, actually, wait. Oh, shit. Uh, Damn, I totally forgot about that. That's cool. All right. Wait, this almost looks right. Okay, wait. Let me. Because look, does it say one, two, or so there's 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8. It's definitely ozonolysis, though. What is this? 3D. Um, all right, so this is a okay. So we have a keto ester. So the first thing we want to do is ethylene glycol to protect it, so that we have an LAH will reduce an ester to an alcohol. It's a very strong reducing agent. Shit. Okay, that one's pretty easy. One, two, three, four, 8. Wait. Oh, this isn't. Oh, um. But I don't even know. I don't even know Wittig. Wittig is so weird. I just wrote it down and I still don't get it. Skip the Wittig one. We gotta keep going. Uh, how do you add a methyl to a... How do you add a methyl to this thing? Okay, let me write down all the problems now. Put them up on my whiteboard so I know which problems I need to do. Actually, I'm just gonna keep going. I don't know F. Wait, I thought that this didn't happen. So I'm not with it right now. Oh. Wait, let's see if this thing works now. Let's go. Oh, this mechanism's long. Okay. Dude, this homework is long, bro. What the hell? I gotta go on another walk. I'm fucking busted.